welcome you all for this video lecture. I am Ramadas, Assistant Professor, Department of Information Technology, Vignan University, Guntur, Andhra Pradesh. So in this video lecture, we are going to see about the finite automata with epsilon transitions. The main objectives of this video, it is going to understand the concept of the automata theory and the theory of computations. And next thing we can go for seeing about what is the formal languages and classes of the languages and their relationship. The outcome after seeing this video, as your students, you can able to understand the concept of epsilon NFA, DFA and subset constructions. So, and demonstrations of that computing the deterministic finite automata and non-deterministic finite automata. So now let's go for see about that. The textbook. What is the textbooks for this author? Author is that Hopcroft and Ullman. Introduction, the subject textbook, the prescribed textbook was the Introduction to Automata Theory, Languages and Computations. So finite automata with epsilon transition. So the epsilon transition with the finite automata. Finite automata is the recognizer which recognizes the input string. So the finite automata is represented in a diagrammatic way, where this finite automata, it will take the input and make the transition from one state into the another state. Whereas in this finite automata with the epsilon transition, so epsilon actually denoted the empty input. It can make the transition from one state into the another state without reading any input. We can use this epsilon transition. So this epsilon transitions we can make any number of times. So in this N of A, we can go with this epsilon transitions. This epsilon transitions is how we can go for moving from one state into that another state without reading any input. So that is called here finite automata with epsilon transitions. So already we have discussed in the previous videos, the finite automata has broadly categorized as two. One is the deterministic finite automata and non-deterministic finite automata. Both finite automata and non-deterministic finite automata, both the recognizing the languages that is called as a regular languages. The languages that is generate the input strings, those input strings are recognized by both finite automata and non-deterministic finite automata. So in this non-deterministic finite automata with epsilon transitions, because the DFA, I mean deterministic finite automata, does not contain any epsilon transition, whereas in non-deterministic finite automata, NFA may contain the epsilon transition. So epsilon means it is an empty input string which is denoted epsilon. We can make a transition from one state into the another state. So now let's go for see the example of this finite automata. In this formal definition, before we enter into that, how we can define the epsilon NFA. So the definition or the formal notations of epsilon NFA is similar to NFA. It's similar to NFA. It contains the tuples like Q sigma, delta, Q naught, F, where the Q is a finite set of states and sigma is a finite set of input symbols and delta is a transition function and Q naught is the starting state and F is a set of final states. Now let's go for see about the example. We have to construct this NFA with the epsilon that accept the language, where the language consists of the strings of any number of A's followed by any number of B's and followed by any number of C's. So what we can understand from this one, the language that contains any number of A's, any number of B's, any number of C's, where the string that contains followed by A, followed by B and followed by C likewise. So we see this finite automata with the epsilon transition. So we have a start state that is called as a Q naught, which contains special arrow mark, that is a start symbol that indicates the starting state, and Q1, Q2. There are 3 states are there. So these 3 states are represented by a circle, whereas the final state or accepting states are represented in a double circle. So in this starting state Q naught, it reads the input A. It contains a self loop. That means after reading this input A, it come back to the same state Q naught. Next input is that epsilon transition. So we can make a move from state Q naught to Q1 with the epsilon transition. So it does not read any input. Instead of that, it read only the epsilon. So we can make a move into the Q1. So in this Q1 state, we can go for applying the input B. The B is, after reading this B, it is that multiple number of B's can be read from this state Q1. So the Q1 that read the input B, it come back to the same state. Similar for Q naught like A. Likewise, the Q1 also B, like that. So the Q1 state, that another one input transition, that is the epsilon transition, we can make a move from Q1 to Q2, where this Q2 is the accepting state, where this accepting state is accepting state which recognize the input C. So after reading this input C, then we can go for multiple number of C's are there. These multiple number of C's are recognized. So what we can understand from this finite state diagram, so any number of A's followed by any number of B's and followed by any number of C's. Next we can see about this in this transition table. It contains the additional entry into that is epsilon entry. So in this epsilon NFA, in the transition table, that one more column is added newly, that is called epsilon transition. So in this epsilon transition also, we can make the details of the epsilon transition from one state into that another state. Now let's go for see the another one example. How can we parse the string in this finite automata like that? So by using the diagram, the finite automata diagram, we can go for parsing this input string. We can take the input string as AA, BB, CC. So the string is AA, BB, CC. So the delta is a mapping function. By using this delta is a mapping function where Q naught is the starting state. Where Q naught is the starting state. From this start state, it read the first input A. It reading this, after reading this the first input A, it come back to the same state, because the Q naught state that contains the input A, after reading this input A, the state come back to the same state, that is called Q naught. Next, the Q naught state, it's read the input B. After reading this input B, there is an epsilon transition. We can go for make it into the Q naught into Q1. So now this Q naught comma epsilon transition, so the transition goes to state Q naught to Q1. So now this mapping function from Q1. So Q1 followed by the input B. So in this B, so after reading this input B, again it will come back to the same state Q1. Similarly, after that, then we can go for this make into the epsilon transition. We can make it into the state Q2, and Q2 state, we can read the input C. Again, it will come back to the self loop, the same state Q2. Again, reading this input, another one C. Then finally, Q2 is the epsilon or the Q2. So Q2 is the final state or accepting state. So then we can announce that the given input string is accepted by this finite automata. So next we can see the another topic is that is the epsilon closure. So how can we find this epsilon closure? So the epsilon closure is a static in all transitions. Out of the states are labeled. So the epsilon closure of the state is set of all states which are reachable from state Q on epsilon transition. That means we can go for computing this epsilon closure. So first we can go for this epsilon closure for this finite automata. In this finite automata, there are three states are there: Q0, Q1, Q2, where Q0 is the starting state. This starting state has reading the input. We can make the input. We can make the transition from Q0 to Q1 using the input epsilon. Likewise, Q1, that is a reading the input transition to Q2. So if we go for finding the epsilon closure of Q0, first we have to initialize the state Q0. Then we have to find the possibilities or the transitions of epsilon from the state Q0. So there is a transition from Q0 to Q1. So we take the state Q1 also included in the epsilon closure. Then after we have to find any other transition possibilities for the same epsilon transition from the state Q1. So the Q1 that have a transition on Q2. So the epsilon closure of Q0 that contains that Q0, Q1 and Q2. Similarly, the epsilon closure of Q1 is Q1 that contains that epsilon transition. So we have to initialize the state first Q1, and this Q1 state we can go for identify the epsilon transition. So there is a transition from Q1 to Q2. So there is we have to include the Q2 also in the epsilon closure. Likewise, we can go for computing this Q2 epsilon closure of Q2. So we have to initialize the same state Q2. There are no other any transitions on epsilon transitions on the state Q2. So the epsilon closure of Q2 that contains only the Q2. So this is the method of computing epsilon closure of the states. So again I repeat this one. So epsilon closure of Q0 means we have to first we have to initialize the state Q0. Then we have to find the possible transitions of epsilon from the state Q0. So we have from this finite state automata, there is a transition. Again we can go to the Q1 because the transition is epsilon from Q0. Then we can go for include this Q2 because there is a epsilon transition from Q1 to Q2 like that. Similarly, we can go for computing this epsilon closure. So now we go for see this one where this Q2 is that accepting state or like that, and any number of inputs are zeros, ones, twos or like that in this state diagram. So now in this one it may read any number of zeros followed by any number of ones and followed by any number of two. So this finite automata that actually it generates the strings. It generates the strings any number of zeros followed by any number of ones and followed by any number of twos. Okay. Now we go for that finding the epsilon closure of the state 1 and epsilon closure of state 2 and epsilon closure of state 5. So this finite automata, it is an epsilon NFA which contains the epsilon transition from the starting state. The starting state is a special arrow mark which indicates that one. So state 1 is a starting state. From this starting state we have an epsilon transition from 1 to state 2 and 2 to 3 and 3 to 6. Similarly from the state 1 to 4 like that. So we can go for finding the epsilon closure of 1 means first we have to initialize this epsilon closure of 1. So from this epsilon closure of 1 there are two possibilities are there for the states. From epsilon closure 1 there is a transition on 2 and 2 to 3 and 3 to 6 similarly and 1 to 4. So the epsilon closure of 1 that contains 1, 2, 3, 4, 6. Next we can go for finding this epsilon closure of 2. So now we can take the state 2. State 2, from this state 2 we have to find this epsilon closure of 2 and first we have to initialize the state 2. Then we can find this epsilon closure of state 2. So there is an epsilon closure transition from 2 to 3. So we have to include 3. From the state 3 there is also the epsilon transition that is called, it goes to state number 6. So we have to include the state 6. So the epsilon closure of 2 that contains 2, 3, 6. And next we can go for find the epsilon closure of 5, where this epsilon closure of 5 that contains the state. First we have to include the state 5. From the state 5 we have to find the epsilon closure. So the epsilon closure is a transition on the state from 5 to 7. So we have to include the state number 7. So the epsilon closure of 5 is that contains 5, 7. Now we can go for construct the NFA without epsilon move from the given NFA with epsilon. So we have to construct this NFA without epsilon move from that with epsilon from this given epsilon. So in this stage we see this diagram in this finite state machine, and there is a transition. The finite state machine, that is a Q0 is the starting state, where this starting state contains the inputs, the A and the epsilon transitions, and the state Q1, the Q1 is the accepting state, it read the input B. So now let's go for finding the epsilon closure of Q0. So then first we have to include this epsilon closure of Q0, this Q0, then transition from Q0 to Q1. So we have to include this epsilon closure of Q0, Q1. Now let's go for finding this epsilon transition or epsilon closure of the state Q0. So we have to find the state Q0, Q1. Next we can go for that applying the input of the Q0, epsilon. So we have to find this epsilon closure of Q0, epsilon. So we have to answer this Q0, Q1. So first we have to apply the input A from the state Q0. So from the state A, it goes to the delta dash, that is the Q0 dash of A. So whereas in epsilon closure, we can go for rewrite this the epsilon closure delta dash of Q0, epsilon followed by the input A. So now let's go for the Q0, epsilon. So the Q0, epsilon is that already we have find out the epsilon closures. That is the answer is Q0, Q1. So now let's go for the input A for the delta of Q0, A union delta of Q1, A. So we can go for that compute the epsilon closure of Q0 union pi symbol. The pi symbol that indicates there is no transition for the input A. So that is empty. So we can denote it as the pi symbol. So epsilon closure is the Q0. So we have answer is Q0, Q1. So this is for the input A. Next we can go for the input B. So this epsilon closure we have to go for the finding this for the input B for the state Q0. From this state Q0, B epsilon closure, the same concept we can apply this one epsilon closure of delta dash of Q0, epsilon. So the Q0, epsilon is we have to find the closure functions of Q0, epsilon. So the closure function of Q0, epsilon is already we found that is Q0, Q1, then followed by the input B. So in this state now we can go for that finding this epsilon closure of delta of Q0, B union delta of Q1, B. So in this case delta of Q0, B. So Q0, B is there is no transition for the input B in the state of Q0. So it is the pi symbol union, and there is a transition for the input B on state Q1. So it come back to the same state, that is answer is Q1. So the epsilon closure of Q1, so answer is the Q1. So that is epsilon closure of Q1, so answer is the Q1. So now let's go for that. We can go for the transition table for this one. For Q0, if you apply the input A, we can get Q0, Q1, and for the input we have the Q1. For the state Q1, there is no transition for this input A, so we denoted pi in this transition table, and Q1 for the input we have this same state, that is Q1. So we see this diagram. In this diagram, there is a N of A without epsilon move for this state. So likewise, we can go for that calculation or finding this, constructing this N of A without epsilon. This is the method or procedure for constructing like that. So let's see this one. This next we can go for see about the equivalence of DFAs and the NFAs. The equivalence both NFA and DFA that accept the same languages. Then the NFA is always a set that containing exactly one state, whereas in the state DFA is after reading the same input. So next we can go for see about the subset constructions NFA to DFA. So previously we seen about that NFA and DFA. Now we can go for this NFA to DFA subset constructions. In this subset constructions, in non-deterministic finite automata, NFA are denoted like that N. N that stands for non-deterministic finite automata. The same the same tuples like Q, sigma, delta, Q naught, comma F. This subscript of N that indicates the non-deterministic finite automata. Similarly, we have to build the deterministic finite automata, which is denoted the subscript D, Q sigma, delta, Q naught, comma F, such that L of D, that is the language of this deterministic finite automata, is equal to the language of this non-deterministic finite automata. So now let's go for see this how to construct this one, this all subsets of Q of N, that is power set, and F of D set of subsets. The equivalence of this NFA, if there is a NFA and DFA accept the same language. For any NFA, there is a DFA that accept the same language. So the number of states in the DFA is exponential in the number of states of NFA. So the NFA accept exactly the regular languages. The subset construction, that is the states are 2 power Q, that is set of subsets of Q. We have 2 power Q states, and starting state as usual is a Q naught, and final state are those that the member of the F. The final state is also the member of the F. So let's see this example. We will construct the deterministic finite automata equivalent to for our chessboard. So the chessboard of NFA. So we have to construct this DFA. So in this one, we have to identify the colors red and black. So in this red and black, first we have to take the first cell, that is 1. We can take the first cell 1. The adjacent cells of red is, we can take the adjacents of red color, or in the transition table, which indicates that adjacent cells of this 1 is 2, 4, because 2 and 4 is the adjacent to that, immediate adjacent to the cell 1. It contains the red color. Similarly, if we go for the B is a black, so adjacent colors of the black is only the 5 for the state 1. Similarly, if we take the state or cell 2, for the cell 2, the adjacent red colors are 4, 6. And for black, it will contains 1, 3, 5. Next, we can take the cell 3. For the cell 3, adjacent red colors are 2, 6. And for adjacent black colors is 5. So, likewise, we can take each cell and finding this, the adjacents of this color, then we have like a finite automata, that is a NFA. We have to, from this NFA, we can go for construct into the DFA. So in this one, let's go for this first state or state 1, there is a red for 2, 4, and from 2, there is a 1, 3, 5 like that. So what I am explaining this one, we can represent it in this form like that. So likewise, every state, there is a adjacent colors are denoted like that. Now the examples moves of this one. The states are squares and the inputs are R, that is moved to an adjacent red square, and the B that moved adjacent black square. So start state, final state are opposite corners. Start state and opposite corners. In this case, we see this as subset constructions of this one. We can take this one from this NFA, we can go for the DFA. So take the first cell for the red color 2,4 and for black color 5. Next we can go for finding this epsilon closure of 2,4. Right? So that is a subset construction. So then we can finding the epsilon closure of 2,4. Then we have an answer is 2, 4, 6, 8. Similarly, for this black color, we may going to find the subset construction, that is the epsilon closures, or for that the adjacent colors is as 1, 3, 5, 7. And next we can go for that, take the 5. For that 5 we can go for adjacent red colors, the same previous one, 2, 4, 6, 8, and that's 1, 3, 7, 9. Similarly, next we can take the 2, 4, 6, 8. Then we can go for finding the adjacent red colors. The answer is same, 2, 4, 6, 8. And the black color is 1, 3, 5, 7, 9. Then this process will be continued until we can go for finding no more new states. So these are all the states like 1, 2, 4, 5, 2, 4, 6, 8, and all. That is adjacence of the red colors and the black colors. That is, we can call this as a state. So this is called as a DFA for that one. Now let's go for see the next example. In this example, the language is L. The L is the language that contains the input string W if it is a non-empty and will end with 0, 1. So this string that end with the 0, 1. So we have to construct that epsilon NFA to DFA. So in this state we have the transition table, the NFA with the epsilon, so epsilon transition like that. Then we may go for finding this epsilon closure. So starting state is a Q0 dash. Q0 dash is a starting state, that is a special arrow mark that indications. And next we can go for that Q0, that reading the input zeros and ones, and Q1 the transition from input 1 to Q0. So we can go for finding that. So in this one, let's see the exercise. We can go for seeing that convert the following NFA to DFA, and second, finding the set of strings are accepted by the finite automata. So these two are the exercise for you all. Now I am going to summarize what we have seen in this lecture. Finite automata with epsilon transitions and epsilon NFA, definitions, transition diagrams, tables, epsilon closures, NFA without epsilon move, equivalence of DFAs and NFAs, and subset constructions. Thank you. Thank you for all.